flat, that means I made all of these probabilities identical, times the probability of the data given k. And you actually, I hate to say this, but you actually have to do this. So you have a set of probabilities k, so if you want to say the likelihood that the thing is a star is just the sum over all the stars divided by the probability of the stars. Total probability of stars. So that's the marginalized likelihood in this model. Now, this model, I think the model, I'm not sure how many, I think there's 50 models that I have. It's of order 50 or 60 models up there that I put up. So this is a 50 or 60 dimensional prior, right? Because I have, say it's 60 models. Then I have 60 of these probabilities that set the full prior probability distribution for my sample. So I do the same thing. I say, what's the probability of the data? Well, the probability of the data is just the sum over all the models. P of k, P of data given k. And then, of course, the probability of the full data set, of the whole data set, is just the product over all the objects. So once again, I can write a full marginalized probability for every object under every template. And that's a scalar, and in that scalar, I can just, that scalar is a function of these 60 numbers, these 60 probabilities, and I can just find the best set of 60 probabilities to explain my data. Any predictions about what's going to happen? Anybody want to venture? I should stop the tape. Oh.
This is still,
Clouds, it could go off at any moment.
it's still from 1973 when the Institute was started.
I know if I broke it, it would be my greatest shame. Although I have some competitor things. Okay, so reminder, here's where we're at. We have these probabilities. Now, I've just shown you on the board that I just eliminated. Actually, I think this room actually has a capability. Oh yeah, I know my house globally. So I've constructed this massive object. It's a scalar that's just the product over all objects, the probability of that object, and then the sum for that object over all templates. So I'm going to optimize this whole thing. This takes a long time because it's a 60-dimensional optimization problem. But I literally just put python.scipy.optimize.fmin on the negative ln total probability and just grind. I had to leave my computer in a cooling bath. That's how I broke my first computer last week. And sure enough, it optimizes. What does it get? Here's what it gets. So now the ink symbol, the symbol size ink is proportional. The amount of ink I used in red is proportional to the amount of probability the model got in the final optimization. I actually have to say, after 5 hours on my laptop, it hadn't actually converged. So this is just where it was after 5 hours. But anyway, you can see, look at what happened. You see how some models get fat and some models disappear? See? Look at those little guys. These little guys here, see, they get very low probabilities because they just aren't needed. And notice how, even though there is data, there's models here, look at that model there, there's data around that model, so you might think, oh, that model's a good model. But actually, when you take the errors into account, oops, that's showing you the answer. The computer decides to downweight those models and only upweight models along this spine. So this relates to this point that I mentioned about specificity versus generality. When you're trying to optimize this overall scalar, the model tries to move into a mode where it does a very good job of predicting the data. So it tries to downweight as many of the models as possible. Meaning, if you're a data point here, and you could be explained by this model, this unpopular model, or you could be explained by this very popular model, the optimizer will try to set things so that you get explained by the more popular model and make that model even more popular.
And the reason is that the sum over the pKs has to add up to unity, so popularity has to come at the expense of somebody
Exactly. Well said, Hogg. They're very beautiful. This probability has to sum to, these probabilities have to sum to 1. So if I can downweight this model, I get to upweight that model, and that benefits all of the data points talking to that model, and only hurts the one that was talking to that previous model. So in general, it upweights. The crazy thing is, this optimization only saw these black points. It saw no tag data, and it saw no high signal to noise data. But look how nicely the models trace the sequence. So the X models all light up on the galaxies, and the O models all light up on the stars. And there's a hell of a lot of confusion right here at the intersection, as you'd expect. The intersection is a true degeneracy. So there's nothing you can do about the intersection, and you'll see the intersection as we go on. But now I have a marginalized model, so now I can recompute my marginalized likelihoods of being a star in a galaxy in this model that is in fact trained on the actual data, which by assumption is the best data you have. And now our contamination has dropped to 12%, and notice that the contamination is very understandable. There's a few objects here that are at the peak of the galaxy locus. They are right on the stellar locus. And then there's objects that are outliers from the galaxy locus, but outliers that hit the star locus exactly. So there's no magic bullet. There is still contamination. However, the contamination is enormously reduced by making a model that actually explains the data. That's the main point. I'll just flash you one more thing, which is sometimes you do have tag data, and this comes back to Hans Walter's question. Imagine we were in a region of the pan-stars data where we did have classifications. Then you can use those to improve your marginalization further. And then we get this outcome, which doesn't necessarily look better, but does do better. So if you do have tag data, you can do even better. So even if some of your data are tagged, so this is fully tagged data. This was learned on fully tagged data. That's what it means by with training. There's a training set here. So the previous method used no tags. But if you have tags, you should use them. And you can do hybrid methods that have some of the data tagged and some not tagged. Yes?
But I would suggest that there's no real fundamental difference between tag data and your models other than the noise in your tag data.
I agree.
Because I mean,
yes,
basically what you're doing is the same, right?
Good, exactly. The models basically are tagged data.
With no noise.
Well, with an assertion of no noise, which turns out to be wrong.
Right.
And really what the hierarchical method is doing is finding the models that are consistent with being no noise tag data. That is what it is doing. So that's how you can see that there's hybrid methods that do whatever you want. Yes?
And so that hole in the distribution near 0, 0 means that if you lie there, no matter how much you look like a star, there are so many galaxies nearby that you can never be sure that there is a star.
That's right. So one of the things, so if you can see there was a bias in this whole presentation because I'm thinking in terms of stars trying to get rid of the galaxies that are poisoning the stars. If that's the attitude, and if you think about it, that's a statement of my utility. Because I plan to do things with the stars that require low contamination. So my utility is pushing me towards methods that reduce the contamination. The low contamination comes at a price. The price is I don't ever see the stars here, because that's where the galaxies are confusing. It's similar to in Sloan, there are some redshifts where quasars look like A stars, and then Sloan just didn't measure many quasars in those redshifts, and that's it.
But where in the algorithm that you implemented the utility ever come in? Where did it come in that you care more about the stars?
So it came in, well, and I never explicitly put that in, it's true. It came in two ways. One is that if you want to get all the stars, and you don't mind about the galaxies, you would use far more stellar models than galaxy models. And then you would have a much denser grid of stars. Stellar models in here, I put comparable numbers of models for the stars and galaxies, even though there weren't comparable numbers of stars and galaxies. And so that effectively was a bias in my system towards excluding the galaxies. If I didn't mind having more contamination, I could have just a rough model for galaxies. I just want to get rid of the galaxies that are really obviously galaxies, but I want to make sure I get every star. And I would have been a very dense grid of models of stars. And as Klaus and company did in Combo 17, you would also, if you wanted, they wanted to get all the galaxies right, so they didn't just put in all the galaxies, the templates they knew about. They also put in those templates with dust added and dust subtracted and with calibration errors and all those things. So if there's one component you care about deeply, you want to really fit up the model space in that for this kind of method.
Is an alternative? I mean, here you label all the things that have a higher probability of being stars than galaxies.
Good.
Right? So you could also set that's a threshold of 50-50.
Exactly. Good, so what I didn't make is the trade-off plot. So in the previous version, I made these trade-off plots where your completeness and purity compete. Same thing here. This is just a cut at 50-50, which is a ridiculous cut. You should obviously pull that cut to where your utility is optimal.
No, I can say this is where your utility comes in.
Exactly.
Using what you plot. If you plot the probabilities,
yeah.
Right? Or if you had taken a cut somewhere else,
yeah.
you could
exactly. I can move the cut down. I can move the cut down so this fills in. And then I can move the cut up and get rid of even those two. That's right. So that's part of it. Yeah.
Can I disagree with something you just said?
Yes.
Because I think we agree on two of them. So, you said that if you wanted to, you said you built in a bias in terms of the ratio of galaxies to stars. Now, I disagree with that. I think what you do, if anything, is you build in a bias towards the galaxies simply because you sample better their cosmic variance. But I don't think the absolute number is coming in here. Because you're optimizing the probabilities, right?
I am not going to disagree with that until I've done some experiments.
Well, I'm not going to agree with it either. That's my feeling, because I suspect if you double the number of galaxies, you can still get the same result, assuming that doubling of the sampling doesn't actually improve the... Sorry, but doubling the number doesn't improve the sampling.
Good.
Right.
Well, so one of the things that's very, very nice about these methods is that in the optimization, so we started with many models, and we ended up with a small number of models that have high probability. It is true that this method will only light up as many models as it needs to explain the data. So if I pour in thousands of times as many galaxies, but they're equally bad, galaxy models that are equally bad as these, it will still light up approximately the same number. It will get them a little bit, because there'll be a higher density of them, it'll get them a little closer to the correct spine. But in fact, because we're doing this marginalization, in the same way that in the first problem, the marginalization removed this freedom of having a radius, the marginalization over many models removes the freedom that there's many different templates representing the galaxies. So in that sense, I think I might be wrong and you might be right on that point. If that connected to what you said.
Yeah, it did. I'm thinking about it.
Could you move on to the general discussion?
Yes, I'm done. I'm actually done. My points are made. My point is that if you want to do classification, you should be doing marginalized likelihood or posterior probabilities. You should construct your prior probabilities that are needed for this marginalization through hierarchical methods, because your data are the best data. There aren't other data you can use to train your models. Thank you.
Thank you very much for this very pleasant talk, covering both the stellar people and the stellar people. Questions, remarks, more questions? Yeah?
Absolutely provocative, but now that I see this final plot, I would have said, doesn't it just tell us that we should forget about models and take sort of an empirical way using colors? I mean, I would have naively drawn these ridges by looking at these observed data and saying, okay, this is the actual color space, and we should use these kind of empirical colors to interpret our measurements.
So, great question, and I'm totally down with that. I think there's a couple of issues. One is that let's go back to the first example. In the first example, the reason we were able to separate the stars and galaxies was not really by having a model of galaxies. Our only idea was that galaxies can have finite size. So then we were just asking